Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams. And today, continuing in our segment about settling the solar system, I want to take a look at the closest planet to our sun, Mercury. That hot, airless, hellish place could actually become a home for humanity someday. The idea has been explored in science fiction, although not nearly as extensively as settling on the moon or on Mars, or creating outposts on other planets, moons, and large asteroids in our solar system. And there's good reason for that. As I said, Mercury is not exactly a hospitable environment. No one would expect it to be, given its proximity to the sun. And yet, with the right strategies, we could actually establish human settlements there that would actually be sizable, self-sustaining, at least to a point, and which could provide the rest of the solar system with abundant mineral wealth and energy, which in fact is why the idea has been explored by futurists and scientists that include the likes of Arthur C. Clarke and Kim Stanley Robinson. So, to address the hellish nature of Mercury first and all the challenges it presents to the establishment of a human outpost there, Mercury orbits our sun at an average distance of about 58 million kilometers, which is roughly 40% the distance between Earth and the sun. So at this distance, it receives 7 times the amount of solar radiation that the Earth does. And because Mercury is airless, which is to say it has no atmosphere to speak of, any exposure to radiation on the surface of Mercury would be unmitigated and very fatal. And while Mercury does have a magnetic field, like Earth, it is much weaker than Earth, so that too is not going to be providing much in the way of protection. Alas, radiation really isn't the most serious threat, but rather the temperature range. Again, because Mercury is an airless body, it has no atmosphere to retain heat or distribute heat, and its slow rotation as well means that one side of the planet will be facing towards the sun for an extended period of time, and the other will be facing off towards space. And while this is happening, the sun-facing side gets extremely hot, reaching temperatures of 427 degrees Celsius, which is about 800 degrees Fahrenheit. Like Venus, that's hot enough to melt lead, and zinc, interestingly enough. So it's certainly more than enough to cook a person alive in their spacesuit. Meanwhile, on the dark side, temperatures will plummet to about minus 173 degrees Celsius, or about minus 280 degrees Fahrenheit. And that's cold enough to freeze dry ice from carbon dioxide, as well as most forms of fuel and alcohol. So basically, the temperature extremes go from hot enough to cook you alive in your spacesuit to cold enough to freeze you solid. And as I said, the orbital characteristics of Mercury, they're really quite weird. And this is true of all planets that orbit very closely to their suns or satellites that orbit closely to their parent bodies. They experience an orbital resonance where the gravity of the parent body, it affects their rotation. So this is the same relationship that Earth and the Moon have. Because of the Earth's gravity, the Moon rotates very slowly, and as a result of that, its orbital period and its rotation on its axis, they're perfectly in sync. So what this means is that one face is constantly pointing towards the Earth as the Moon orbits around it. And this is why we refer to the Moon as having a light side and a dark side. Technically speaking, the dark side is not dark. It picks up plenty of illumination from the sun as it orbits Earth, but because we can't see it, we know it as the dark side. And this phenomenon is known as tidal locking. or an orbital resonance of 1 to 1. In Mercury's case, it's a little bit different. It has an orbital resonance of 3 to 2, which means that for every 3 rotations that it makes on its axis, it will make 2 orbital periods around the Sun. So basically, Mercury will take 88 days to complete a single orbital period, but takes a little over 58.5 days to complete a single rotation. And so you might be thinking that this means that a year on Mercury is 88 days and a day is just shy of 60. But in fact, due to the nature of its orbital mechanics, again, a solar day, which is the amount of time it takes for the Sun to return to the same place in the sky. So if we were measuring that on Earth, from 12 noon on day 1 to 12 noon on day 2, that's a single solar day. And on Earth, that takes 24 hours. But on Mercury, that takes 176 days. So as it's orbiting around the Sun, if it were possible to stand on the sun-facing side, you would see the Sun rise in the east and move slowly towards the west, reversing course several times over the course of the day. And eventually, after 176 days had passed, it would finally set in the west. And then you could look forward to 176 days of perpetual darkness. So this, above all, highlights why Mercury is uninhabitable. For 176 days straight, one side is exposed to temperatures hot enough to melt metal and radiation so intense it will kill anything that moves, to extreme cold for another 176 days straight. And yet, surprisingly enough, it's the same orbital mechanics that actually offer some solutions. Now, whereas no known technology could sustain human beings on the sun-facing side, at least not on the surface, humans could conceivably live on the night side. We have the technology right now to keep astronauts warm and safe in the extreme cold environment of space, on the Moon, on Mars. We've been doing it in low Earth orbit and in cislunar space for decades. So we could build surface habitats on the night side. However, these would have to stay in motion. They'd have to be mobile in order to stay ahead of the boundary between day and night, known as the terminator. And given that Mercury has a very, very long solar day, they wouldn't have to be moving particularly fast, and they would be able to stop and draw resources from whatever location they came to at any given time. And given the fact that Mercury is so very rich in mineral resources, even its surface is believed to be littered with caches of metals, including precious metals and rare earth metals, that have been deposited there over the course of billions of years by impactors. So the settlement, adapted for mining, it could extract a considerable amount of wealth at every stop and just keep going. And this wealth could be used to pay for all the necessities, everything that would need to be imported, that could not be harvested or grown or assembled there on Mercury. And even more importantly, there's the cratered regions around the poles. Whereas Earth has an axial tilt of almost 24 degrees, which is why we experience seasonal changes, Mercury has virtually no axial tilt whatsoever. And this means that the polar regions, which are heavily cratered, they are in a perpetual state of twilight. And within the craters themselves, they're permanently shadowed. And as NASA's MESSENGER probe revealed when it was studying Mercury between 2008 and 2009, there are large concentrations of water ice in these craters, which has managed to stay in ice form because it's permanently shadowed. So here too, bases could be established. They would have to be heavily insulated and shielded, but they would have abundant access to water. They would be protected from the radiation from the elements, the vacuum of space. And from there, mining missions could be dispatched to travel south or north of the polar region there on the night side to extract ore and bring it back to the poles, where it could be launched into space without too much difficulty and transported to other locations across the solar system. And this could be done with relative ease because Mercury's gravity is about the same as Mars, roughly 38% of Earth normal, or 0.38 g, And so the escape velocity, the amount of energy you need to generate in order to get into space from the surface, is less than half 2. And the abundance of water ice means that refueling stations could be established in these craters. You could have automated harvesters gathering the water ice and breaking it down into hydrogen and liquid oxygen. And this could be used to refuel rockets as they come and go, carrying ore and mineral wealth to the rest of the system. Or you could forego that in favor of establishing larger settlements in these craters and using that water ice to not only irrigate crops, but to create oxygen gas, and of course as a supply of drinking water for settlers. Given the volumes of ice, there'd still be plenty left around for refueling operations if the locals were so inclined, although kinetic launchers would probably work better, so using centrifuges that could launch payloads into orbit, or magnetic rails like the slingatron concept. You just bring a payload around and around and around in a widening circle that eventually aims off into space. You could send payloads to orbit around Mercury where they could be picked up without the concern about rocket fuel or refueling stations. And a particularly adventurous idea is that you could also enclose, either in whole or in part, some of these craters, and using some carefully positioned solar mirrors around the edge of the crater, you could then redirect sunlight into it, which would then warm up the environment and melt any water ice contained there, and it would also release the organic molecules, which the MESSENGER probe also happened to notice while surveying these craters on Mercury. And this would be the first step in creating a living biome within these domes. So the settlers could then move in, establish habitats, cultivate the regolith, the soil there, and it would have been irrigated, and along with the organic molecules that are being introduced and probably some nutrient solutions, they'd have viable soil. And then they could begin tilling that and using it to grow their own food. And gradually, all kinds of life forms could be introduced to stabilize the soil and create a water cycle and a carbon cycle and a nitrogen cycle that would further enrich the soil and create a regenerative environment. So you'd have a self-sustaining settlement at that point, and you could create several within the same crater, and they could be connected to other craters and their habitats. And from there, crews could then leave and head out onto the surface with mining vehicles, and remaining on the night side, they could mine all kinds of base metals, precious metals, rare earth metals, and then bring them back to the poles where they could be shipped out. At the same time, space-based solar arrays could be positioned so that they're catching light from the sun 24/7, but not so much that they'd be overwhelmed and completely destroyed. And these would not only be able to provide abundant energy to the surface habitats down in the craters, but some could even be beamed off-world to other locations, to receiving stations around Venus, around the Moon, around Earth, even Mars. So over time, a thriving economy could be built on minerals and energy, and on top of that, there's also the possibility of establishing settlements within stable lava tubes, which have been observed on Mercury, much like on Earth and the Moon and Mars. These tubes were the result of volcanic activity, which existed on Mercury at one time, and this was several billion years ago, but nevertheless, along with a lot of other evidence of volcanic activity, it's been very perfectly preserved there on Mercury's airless surface. And so these tubes, which once had magma and lava pushing through them, but are now cooled and empty, they could be the site of future cities because of their spacious nature and really elongated nature. Entire settlements could be built, and they could be walled off and then pressurized, and it would provide additional protection against radiation and the elements. They could quite possibly be used to connect crater settlements, habitats on the surface, and for transportation networks. And so over time, it would be possible to not only create a thriving economy on Mercury based on the export of tremendous mineral wealth and also the export of energy, but also real estate could actually become a viable option, and you could have a thriving settlement on this world. And this would give rise to a new segment of the population known as Hermians. And that name, of course, comes from the name Hermes, which is the Greek equivalent to the Roman Mercury. And the first time I encountered that name, interestingly enough, was in Rendezvous with Rama by Arthur C. Clarke. And that stuck with me over the years. I became very fascinated by the idea that someday human beings could actually settle on Mercury and be called that very thing. And they would join Terrans and Martians and Lunites, likely, or Selenians for living on the moon, with Cytherians, which is what we'd call people living on Venus, which is also derived from classical Greco-Roman mythology. And beyond Arthur C. Clarke, the idea of having settlements on Mercury that would be mobile in order to stay ahead of the sun, this was also explored by several other science fiction writers, not the least of which was Kim Stanley Robinson in his book 2312. And in this book, the city, called Terminator, and the city was always close to the Terminator, and this is how it kept moving. Heat from the sun would warm the rails up, causing them to expand, which would push the settlement onward. And this way, the population was able to stay ahead of the sun and harmful radiation the entire time. And given that craters on Mars were named for great composers and intellectuals and writers, it is likely that Hermians would be artistically inclined and known for the export of their art and ideas. So as with settling the moon, Mars, Venus, settling on Mercury, creating a thriving outpost of civilization there, it's entirely possible. It's just a matter of having the right know-how, leveraging the local resources, and bringing the right technologies, and the right commitment. Because, once again, this is something that would take generations to happen. And the kind of ideas and cultural patterns and new identities that would emerge from it would be nothing if not fascinating. Like, incredibly so. And so, that effectively wraps up this segment when it comes to the inner solar system. Next time, I want to start getting into the outer solar system. Starting with the main asteroid belt, which is basically the boundary between the inner and outer solar regions, otherwise known as the frost line, beyond which planets and moons form from volatiles and gases for the most part, where we have the gas giants and their icy moons. They're not terrestrial in nature, which is to say rocky, composed of silicate minerals and metals for the most part. And within the asteroid belt, within this boundary region, there are several large bodies and abundant resources that could once again lead to the creation of a thriving outpost of civilization, a robust economy, and a post-scarcity future. So stay tuned for that. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.